Hi, I'm Kim Williams from Kansas State University, and this eGrow University presentation focuses on getting water to crops. We'll consider how to make decisions about irrigating and methods of providing water to crops. The topics that we'll touch on include deciding when to water, some key aspects of deciding how much to water, and a brief overview of irrigation methods that are covered in a little more detail in other eGrow presentations. It's tough to overstate the importance of water to the function and growth of plants, and by extension, the importance of carefully irrigating. Water is necessary for every metabolic process performed by plants. Photosynthesis, respiration, everything. Nutrients dissolved in water are absorbed from the root medium and then taken up by roots and moved to shoots in a stream of water. So even if nutrients are present, if they're not dissolved and floating around in the substrate solution, then roots can't absorb them. And the process of transpiration, which involves evaporation of water from the plant's leaves, is how the plant cools itself. Watering or irrigating crops is the greenhouse practice that most frequently results in loss of crop quality. A grower makes decisions about when to water as well as the amount of water to apply. These decisions take skill and training because the grower is balancing crop-specific requirements with interactions of the substrate and fertilization program. These relationships are described more in an eGrow presentation about the nutrient management triangle. So think about it. Who should be making the decisions about when and how much to water? Arguably, watering should be carefully managed by a knowledgeable and well-trained grower. In many operations that have automated irrigation systems in place, only 1 or 2 people make irrigation decisions for the entire operation. The point is that it's a bad idea to put a watering wand in the hand of a brand new employee and then tell them to go water a section. Instead, careful and thorough training is necessary to ensure that each employee who waters understands how to make decisions about when and how much to water. Knowing when to irrigate requires skill. When plants are underwatered, they wilt, which is another way of saying that the foliage loses turgidity, as seen in the photo of the hydrangea in this slide. When this happens, photosynthesis, which is growth, slows. Also, smaller leaves and internodes develop because cell expansion is limited. In more extreme cases of dry down, you may even see leaf margins becoming brown or necrotic, and with some plant species, like Ficus benjamina, leaves may drop. Alternatively, let's recall the effects of plants on plants that are overwatered. New growth is large and lush because, as we think about it, cell expansion is not restricted, so individual cells get very large, the opposite of what happens when water is restricted. Plants are not toned, so they tend to wilt more quickly in bright light and during shipping. And plants are predisposed to infection from root rot pathogens, and a damaged root system is going to lead to plant wilt because water can't be absorbed, but also potentially nutrient deficiency because a damaged root system also results in a limitation of plants being able to absorb nutrients as well. A key point here is that both over and underwatering result in the symptom of wilt. Excessive salt levels in the substrate can contribute to a damaged root system and thus wilt as well. Even high temperatures and bright light that drives rapid plant transpiration may contribute to plant wilt, even though the substrate is well moistened. So you can't just look at a wilted plant and decide that it needs to be irrigated, because the problem may in fact be that the plant is wilting due to other factors, and by watering it, it would just exacerbate the problem. A knowledgeable grower will evaluate the substrate as well as the plant appearance before deciding to irrigate. So, what might we consider some rules of watering? We should begin with a substrate that provides adequate aeration for our given crop and container. If the irrigation system allows, we usually want to avoid wetting the foliage just to help minimize foliar disease problems. We should water just before plant moisture stress occurs, which is based not only on plant appearance, but also on the color and the weight of the substrate. It's often considered good watering practice to irrigate a crop thoroughly at each irrigation, That is, not just spritz the surface of the substrate, but moisten the entire root zone. Now, this rule is broken if the root medium is really tight, for example, because of a soil or clay amendment. Leaching fraction should be known and managed, and I'll discuss this briefly in a few minutes. So, based on this information, would you say that you overwater by applying too much water during a single irrigation event? Can you overwater by applying too much water at one time? The answer is not usually. When a crop is overwatered, it usually happens because the crop has been irrigated too frequently, not because too much irrigation solution has been applied at any given time. Before we get too much further, let's just say up front that rules are made to be broken because in the end, the best managed irrigation takes into account substrate and fertilization, as well as crop-specific requirements and environmental conditions. This is discussed more in the eGrow presentation about the nutrient management triangle. But let's consider a couple of examples. With the poinsettia crop that's sub-irrigated on the left, the grower does not allow the entire substrate volume to wet up at each irrigation to avoid overwatering and root rot problems. Similarly, the grower of the potted geraniums on the right uses a really heavy substrate that contains about 8% soil by volume with drip irrigation, and this really tight mix grows better geraniums when it's not wetted thoroughly at each irrigation, which would keep the root system too wet for too long. So, knowing how much to water is really a balance of crop-specific requirements and the substrate that's being used, the stage of plant development. And we can talk about rules of irrigation, but the fact is sometimes rules are made to be broken, and this needs to be a part of the training and discussion as new growers are trained with regard to how to do irrigation. Now let's take a quick look at leaching fraction, which defines the amount of water a grower allows to drain out of the bottom of a container in an open irrigation system. It's easily determined by capturing the solution leached and dividing that number by the volume of irrigation solution applied. The lower the leaching fraction, the more fertilizer salts will build up in the container. While a textbook leaching fraction is only 10 to 15%, the reality is that most growers who overhead irrigate apply higher leaching fractions, and the majority of these growers do not have any idea what their typical leaching fraction is. So if you're willing just to take a little bit of time to get a handle on your leaching percentage, it can really help you guide decisions such as the rate of fertilizer to apply. It can also help you see where you can save water and nutrients by reducing your leaching fraction and thus lowering the rate of fertilizer that you might need to be using in your open irrigation system. So let's brainstorm now the factors that influence irrigation frequency. What's on your list? I encourage you to pause this presentation and think about what your experiences lead you to include as contributors to determining how much time to allow between irrigation applications. The list of factors that interact to influence irrigation frequency is a long one. Some obvious items on it include the substrate and how tight or loose it is, as we were speaking about a moment ago. The weather. If it's an overcast day and a cooler day, then the need to irrigate is going to be decreased because plant transpiration is slower. Species-specific preferences also certainly come into play. And if the plant is large compared to the size of the container, then more frequent irrigation will be needed. If ventilation or air movement is excessive, this will increase plant transpiration and water use, and thus the need for more frequent irrigation. Checking each bench or production zone twice a day, once in the morning and once in the early afternoon, is typically deemed adequate for determining irrigation frequency. Now let me throw the ball into your court with a question. If a grower wants to speed the drying down of a tight substrate, what might they do? One strategy would be to apply some bottom heat to the root zone. The point is that everything is connected, and managing irrigation is a lot more challenging than just slopping water onto pots. There are a few ways that we can categorize irrigation systems. One is by considering whether it is open or closed. An open system allows water or fertilizer solution to pass through the substrate, through holes in the bottom of the pot, so that nutrients leach into the environment. A closed system is one in which the fertilizer solution is recirculated. Nutrients do not leach into the environment except perhaps when the nutrient solution tanks are emptied. As we turn our attention to an overview of the various types of irrigation systems used in greenhouse production, there are a handful of questions that can be answered about each to allow for basic comparisons. First, how effective and efficient is the system at delivering water to the target of the root zone of a crop? Second, does the system promote pest management problems? Third, does the system minimize environmental impact from water and nutrient loss? Fourth, can the system be used with a variety of crops and container sizes, which is indicated with the term flexibility? And fifth, how expensive is the system to install? We'll use this same framework of 5 questions to quickly compare a range of irrigation systems that are available for use in greenhouse cropping systems. Let's start with hand watering, which is an open system. This favorite means of irrigating certainly is flexible. Most of the water applied hits the target, and as an open irrigation system in which it's difficult to manage leaching fraction, environmental impact is medium to high, especially when soluble fertilizer is being applied. In thinking about the cost of hand watering, the misnomer is that it's not expensive. And it's true that the cost of a wand and a breaker are negligible, but when you factor in the cost to hand water day in and day out, it becomes one of the most expensive ways to irrigate. With simple calculations, which we'll cover in a upcoming eGrow presentation, it can cost easily $1,000 a year to pay the labor to irrigate a 4-foot by 100-foot bench. And labor costs and saving labor costs is as compelling a reason as any to consider automating irrigation. The first grouping of automated irrigation systems is mechanical overhead delivery, and these are all open systems. These open irrigation systems include overhead sprinklers that deliver water and/or nutrients overhead to a large area. A significant drawback of this type of system is that their efficiency is pretty low as 5%, some research shows, depending on pot spacing and how much water rolls off the foliage, and that does contribute to high environmental impact. Cost is low to medium, depending on whether or not systems like hanging emitters are used, like at this garden center, or riser pipes, such as the Rainbird system, which is in this highly automated production operation, or riser pipes used to irrigate on-ground perennials production. Riser pipes are seen here, used in bedding plant flat and potted crop production spaces. Different types of nozzles also influence cost. The systems are very flexible in terms of use with different crops and container sizes, but foliage and flowers do get wet, potentially leading to disease problems. Boom irrigation is an open system it's a popular way to irrigate plugs and bedding plants, as well as to provide moving mist for rooting cuttings or cutting establishment, especially when the plants are set on top of bottom heat. It can be costly to install booms in each production bay, but booms have really good flexibility in terms of being able to use them with various container sizes and plant spacings. Efficiency of delivering water to the plants depends on container spacing. The misting potential of booms, as well as the ease with which they allow for automating irrigation, make them really popular for small containers and for rooting cuttings. Now, as we shift gears to consider more open irrigation systems that deliver water to the substrate surface, we could mention in passing that irrigation tape and perimeter irrigation systems are sometimes used for cut flower cropping systems. When focused on potted crop production, and especially hanging baskets, dribble or drip tube emitters are still very popular. That's not to say that you couldn't deliver fertilizer solution to cut flower crop through drip tubes, as seen on the left, but more commonly potted crops are used with this system, as shown on the right. Because the microtubes are spaced to deliver fertilizer solution to crops at a given pot spacing, a system is designed to be used with a specific pot size, and 5-inch pots are typically considered the smallest for which it's cost effective to put in microtube, drip, or dribble tube emitters. There are many different breakers on the ends of the microtubes. The yellow plastic Chapin breakers in the left photo are no longer manufactured. Metal weights are also an older style of breaker. Many microtubes deliver systems that systems that allow for pressure compensation, so that the same amount of solution is delivered through the microtube regardless of distance of the pot from the point of water delivery, for example. Spray stakes are an adaptation of drip tubes that deliver irrigation solution to cover more surface area of the substrate. The advantages and disadvantages of this type of open irrigation system is really comparable to dribble tubes. The next group of irrigation systems are those that deliver water and nutrients through uptake via holes in the bottom of the pot. The first of these is capillary mats, which may be either open or closed, depending on whether the edge of the mat hangs over the end of the bench and drains via gravity, which would make it an open system. If water and nutrients are contained, the system is closed. Interactions with substrate porosity influence how well this type of system works, and root rot diseases can be a problem if the mat is not allowed to dry down adequately between irrigations. The next type of sub-irrigation system is ebb and flood benches, which is a closed system. Though it's one of the most expensive to install, it efficiently uses water nutrients and has minimal environmental impact. Finally, flood floors are an excellent closed sub-irrigation system, with all of the benefits and most of the cost of the ebb and flood benches. They provide maximum space use efficiency and are often paired with boom irrigation to provide a range of open irrigation options within a bay. More detail about using each of the irrigation system types will be delivered in other lectures that focus on watering potted crops or bedding plants and plugs. A final thought in this irrigation systems overview is to think about how to efficiently water crops in right after potting, and then also just before shipping, which are two critical times to get the job done right. You can see options for automating watering in with the water tunnel at the end of the potting line on the right, and watering just before shipping out, the carts on the left. Watering crops is an underappreciated aspect of greenhouse plant production in terms of its complexity and impact on producing high-quality crops. While we barely scratched the surface of this topic in this presentation, hopefully this overview helped you think about different ways in which watering can be accomplished. Thanks to the Glockner Foundation and all of the partnering institutions for supporting eGrow University.